What's so special about factored form of a polynomial? Up until now, we've seen expanded form. So we've seen things that look maybe something like y equals 3x to the 4 plus 2x cubed minus 2x plus 1, something like that, expanded form. This form is good for algebra. It's pretty easy to do algebra with. It's good for calculus, but it's not so good for sketching a graph. It's difficult to sketch a graph from something that looks like that. You probably wouldn't even know where to get started, and it's not easy. So instead, we have factored form. And we're used to seeing factored form for quadratics from grade 10 and 11, basically. So we're used to seeing something like this: y equals 3x minus 2, x plus 4, for example. What does that mean? Well, we know from that we would be able to sketch the graph of that function, right? So if we have a quadratic with that shape, remember these two things are the zeros, right? Or tell us what the zeros are. They're the factors, but they tell us what the zeros are. So this actually tells us we have a 0 of 2, right? And a 0 of negative 4. So just a rough sketch here. The 3 tells us the direction it opens, so it opens up. So roughly something like that. That's what we would do with parabolas, and we're used to seeing stuff like that. But what about something like this? So I have a function here, and this function has 3 x's, x, 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 which means it's probably a cubic function, right? And a few things we know about this right off the bat. So the leading coefficient is going to be the first term, right? Or the term with the highest power. So if we wanted to see what that is, we could think about if we multiplied all the x terms together. So we multiply x times x times x, and then times that 3 out in front, we'd end up with our first term being 3x cubed, right? So our highest term would actually be 3x cubed, right? Or our term with the highest power. So our leading coefficient here, this tells us is going to be 3, which is the same as just the initial value here. The zeros, what do you think the zeros are going to be of this equation? If we look back at our quadratic, the zeros were just whatever made these two things equal to 0. And it actually doesn't matter what the order or the degree of the function is, that's always going to be true. So the zeros of the function can be found from here. So x minus 2, what's the 0 that's going to correspond to that? 2. What's the 0 that's going to correspond to the x plus 1? That's going to be negative 1. And then the third 0 is just going to be negative 3, because those are the three things that make this function equal to 0. And we also know our degree of our function, based on the fact that there's 3 x's in there, is going to be 3. So just in general, that's what's here on the left. In general, we can have a function with an a value in front, which is going to be our leading coefficient, and there's x's in each set of brackets with the zeros, p, q, r. You can keep on going. You could have 4, you could have 5, you could have 6 zeros. It doesn't really matter. It's always going to follow this pattern. And to find the degree, you can just count the x's. How many x's do we have involved in the function? So let's take what we know about quadratics, and let's try to graph this function up here with the same sort of idea. Okay, so we're going to graph this one on this grid here. So I'm just going to set up a little grid real quick. You can use a ruler to make it nice. So we said our 3 zeros are going to be 2, negative 1, and negative 3. So I'm just going to put those in. 2, negative 1, and negative 3. So those are going to be our 3 zeros. Now the question is, we know it's going to touch those 3 points, but what's it going to look like in between? We know cubics sometimes have a look like that, sometimes they look like that, sometimes they look just like that, or like that. So what shape is it going to be here? Well, because it has these 3 zeros, we know it's probably going to look either like this or like this, because it's going to have to sort of go down and up and down again. It's not going to be sort of this smooth little curve here. But the question is, where does it start? Does it start in the bottom left quadrant, or does it start in the top, or the top left quadrant, right? Does it start up here or down here and go like this or like this? Well, if you think back to what our leading coefficient tells us about this function, think about the fact that it's positive. First of all, our leading coefficient is positive, right? So what does a regular cubic function look like, right? Because it's positive, and we know a regular cubic function looks something along the lines of this or this, right? It's a negative one would start in the top left, right? But a regular one with a positive a value would look like this or like this. So that tells us it's probably going to look something like, I'm going to do this in a light yellow color because we might change it after. It's probably going to look something like that, right? And that's what our a value tells us. But can we be a little bit more accurate about this graph? Is there one other thing we can do to be a little bit more accurate? And usually, just as a bit of a check and a way to be a little more accurate, one other point we can find is the y-intercept. We have the three x-intercepts, but it's also convenient to plot the y-intercepts. So the y-intercept occurs where what? Well, we know the y-intercept is going to occur where the x value is 0, right? It's going to be right here where x is 0. So I can find the y-intercept by setting basically x equals 0. So basically I'm going to find f at 0. What does that give me? And if I look back on my equation, that's going to be 3. It's going to be 0 minus 2, which is minus 2. Oops. And it's going to be 0 plus 1, which is 1. And then 0 plus 3, which is 3. So our y-intercept is going to be negative 18. Now, if we look at our graph, I didn't really draw that to scale or anything, right? But, and sort of what I've done so far is the rough work. I haven't labeled any of the axes or any of the scale or anything like that. So in order to sort of complete this graph and make it a little bit more accurate, why don't we just label this point here as negative 18? And we can label this as 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4. You can be neater about this. It's a little bit hard to do on an iPad, but you get the idea, right? So our x-axis and our y-axis don't have to have the same scale, which is fine. It just makes it a lot easier to sketch. So now we have a bit of an accurate graph. And finding the negative 18 was also useful because what it did is it allowed us to check our work, right? We assumed, based on the a value, it was going to go like this, right? What if we had found that the y-intercept was supposed to be up here? Well, that probably would tell us that we graphed it going the wrong way, right? So finding the y-intercept not only makes the graph a little bit more accurate, but it's also a way of checking to see if your a value made the function go the right way. So just in general, when you're asked to find or to sketch the graph of a function from its factored form, we should be including all the zeros as well as the y-intercept. So basically all the x-intercepts and all the y-intercepts. Well, there's only ever going to be one y-intercept, but you should always plot that as well. Okay, so we know how to go from the equation in factored form to the sketch of the graph. Can we go the other way now? Can we start with the sketch of the graph, or an accurate graph, and then find what equation models that function? And before we actually dive into that, let's go back up to our example of our quadratic up here, right? Could we do this for a quadratic? I think we could, right? And the way we might do that is we might identify what those zeros are, and then we would plug them into sort of the general form of a quadratic in factored form. And we're going to do the same thing here. We'll save the a part for after, but we're going to do the same thing down here. Okay, so what are the zeros of this function? The zeros of the function are, just zooming in here, there's going to be negative 2, so negative 2, 1, and 2. Those are our three zeros. So if we think about what the equation is going to look like based on this, we're going to have y equals, and it looks like a cubic, right? It has three zeros here. So it's going to be x, and then we have to switch the sign. Remember when we go from the zeros to the equation? So it's going to be x plus 2 for our first zero, x minus 1 for our second zero, and x minus 2 for our third zero. And remember the reason for that, the reason why it's a plus sign here, but the 0 is negative 2, is because these are the three things that make this equation equal to 0. right? So if we plugged in that -2 here, it would make this equal to 0, which makes the equation equal to 0, which is exactly what a 0 is. It makes the equation equal to 0. Are we missing anything from this part of the equation, or from this equation? And the answer is, yeah, it's right above there. We left out the a value. Do we know what the a value is? Not yet. So we're just going to leave that as an a there at the beginning. You can probably, if you're thinking a little bit ahead, you can probably guess what direction or what sign the a value has, if it's positive or negative, but I'll leave that up to you to think about. So what we know now is we know an equation of the family of functions that passes through those 3 zeros, right? So we haven't pinned down an a value yet, right? So for example, we could be describing the equation that looks like this. It goes through those same zeros. Oops. Let me, that was not good. See how it didn't go through the zeros there? I'm going to fix that. So maybe it went through like that. Ooh, I'm not very good at this, am I? Sort of difficult to do on an iPad. Maybe it went through these 3 zeros like that. Or maybe it went through the 3 zeros like this. Right? The a value is what's gonna basically determine that's it's this exact red line here, right? So we call those different functions, the ones that have the same zeros but different a values, we call that a family of functions. So they have the same zeros but different a values. So basically I already did this part here. And as I said before, if you're thinking a little bit ahead, you can determine what the a value would be. So for the red one there, we know that the a value, because it's like a regular cubic function, starts down here in the bottom left, right? Up, down, up, finishes in the top right. So that's probably going to have a positive a value, right? Here, this one that starts in the top left, goes down, up, down. That one's probably going to have a negative a value because it goes the opposite way. And that third one that I drew, this one's not quite as stretched, right? So it's going to have a smaller a value. It's also going to have a positive a value, right? Because it still starts and finishes in the same quadrant as that red one. But it's going to be a little bit smaller because it's not as stretched. Okay? So that's the answer to number 2. So now let's determine the exact a value. Okay? So we do that by finding another point on the line, just like we do with a parabola in grade 10. Find another point on the line and plug that into the equation we already have. And an easy point from this graph is obviously this point here, the y-intercept at 0, 2. Convenient to use the y-intercept when you can, because obviously the x part of that coordinate is going to be 0, and whenever you plug 0 into an equation, it's going to be a little bit easier. So let's plug that into our equation. The y part is 2, and the the x values are 0. So a, 0 plus 2, 0 minus 1, 0 minus 2. There we go, and we can just simplify and solve this equation. So that's going to be a times 2 times -1 times -2. So it's basically 2 times 2, which is 4. So our a value, if we divide by 4, is going to be 1/2. Okay? So our final equation for this, for that red graph there, is going to be y equals 1/2 x plus 2 x minus 1 x minus 2. Okay? I like to keep it as a fraction when it's a nice simple fraction like that. It's an exact answer, and you don't have to deal with decimals. I'm also just going to put a nice little box around that because it's our final equation. And by the way, just to check, our a value did end up being positive, right? Which is what we guessed it would be based on the fact that it starts down here and finishes up here. Okay? So you should always just do a quick check to make sure it's the right sign afterwards. So in general, here's our summary. In order to determine an equation, identify the zeros and plug them into the equation, the general form of the equation, and then plug in a point to find a. And there you go. Not much more complicated than with a parabola. Now, this isn't the end of the story. We do have a little bit more. So if you look at the handout, it does continue with something called factor order. So it's not always going to be this simple, but we're going to save that for an activity in class.